Well, welcome everyone to GeoHug. So I'm so excited to have Bruce Gemmell joining us this week. Bruce was the head of School of the Earth Sciences and Director of Codes at the University of Tasmania for over 30 years, and he's since become a consultant to the minerals industry. And Bruce has conducted research on a number of ore deposit types, so it's going to be fantastic to hear from him today about VHMS deposits and their exploration potential. So thank you so much, Bruce, for joining. It's amazing to have you. Thank you.
Well, thanks for the invitation, Jess. I look forward to it. And I can certainly see a lot of old friends in the little sort of boxes here and people I haven't seen for a long time, etc. So let's have some fun with this talk. Okay, well, good afternoon or good morning or good evening, wherever everybody is. And it's a pleasure to be here today. And I've got about 40 to 45 minutes to try to tell you a lot about VHMS deposits. I've been fortunate enough to work on this type of deposit for most of my academic career and in exploration before that. They're fascinating types of deposits. They're they're not a new exploration target, but they're being reinvigorated around the world in the industry right now. We'll talk a little bit about that near the end of the talk. But they're also one of the only styles of mineralization you can actually see forming in front of your eyes. That is, if you're fortunate enough to be able to get down to the bottom of the ocean in a submersible, or have a camera down there that's looking at the famous black and white smokers. And we'll touch a little bit on those towards the end of the talk as well. So these are really important styles of mineralization. I think they've been underappreciated for about the last 20 years, but they're coming back into vogue now. So what I'm going to do in the talk is talk about the geological attributes of this style of mineralization. We'll touch on the genesis, how and why they form, and why there are differences, because this is a whole family of deposit styles, not just one size fits all by any means. And then we'll go a little bit into what I think are some of the important criteria for exploration and some of the exploration potential we've got around the place for this style of mineralization. All right. Okay. There is a bit of a confusing nomenclature when it comes to this style of mineralization. They're lovingly known as volcanogenic massive sulfides, primarily in North America. That's where that term came from. Here in Australia, our group from the University of Tas really sort of pushed the volcanic-hosted massive sulfide, simply because that's a term that talks about its host environment, whereas volcanogenic is actually a genetic term for it. VAMS came out of the Canadian group for a while, volcanic-associated massive sulfide. Some people like that, others don't, but it hasn't really caught on like the first two. And then over about the last 25 years, there's been a lot of work on the modern seafloor where the black smoker systems and some potential mineral deposits have been found on the seafloor. And the companies that worked on those coined the term SMS, or seafloor massive sulfide, as if this was something new and magical compared to what we knew from the ancient deposits on land. They're not, they're corollaries of the ones we see on land, and I'll touch a little bit on that towards the end. What makes these attractive deposits is mostly they're polymetallic. They may not have all 5 of those major elements as shown in this diagram, but they usually have at least 2 or 3. And depending on the prices of metal, et cetera, at times, you can ride out some of the hard times with some of the other metals you've got in your deposit. But also importantly, what I've listed there are the minor elements. And some of these are now becoming very important as we get into the whole green metals industry, et cetera, and looking for these byproduct type things. And there's a lot of these elements that do occur in the minerals in these deposits. And interestingly enough, some of it reports to the concentrate, but there's actually an awful lot that actually ends up reporting to tailings. And there are groups now going around reevaluating tailings and even, in fact, mining tailings to try to get either the major metals out or look for some of these minor metals. We know of about 1,100 deposits or major occurrences of this style of mineralization on the crust, but that's only 30% of the Earth right now, at least it's above sea level. Underwater, we know of about 700 occurrences. I wouldn't even put them as deposits or major. There's about 4 or 5 you could even put in the deposit category right now, but that's simply because exploration on the modern seafloor is actually very difficult. As far as economics go, we've produced a huge amount of volume of tonnage of sulfide ore from these deposits. They are really known as zinc deposits. About 22% of the world's zinc are won from VHMS deposits. You can see the other values going down there. A lot of lead, interestingly enough, and 2.2% of the world's gold, which is important at the same as well. But they are very often truly polymetallic styles. Sometimes they're one metal or the other, like gold only or copper only, but for the most part, they're polymetallic style of mineralization. Most of you, when you first studied or were taught about VHMS deposits, probably had diagrams that looked like this put in front of you. They're great. There are deposits that look like this. We call these the mound-style deposits. But what I want you to take away from this by the end of the talk is not all VHMS deposits look like this at all. It's one style, the mound style, which is basically the blob of massive sulfide sitting on a carrot-shaped feeder zone, or a pipe-shaped feeder zone with a stringer zone in that, which is the plumbing system bringing the fluids up to or at the seafloor position. On the left-hand side is the ancient example. This comes out of one of the Noranda deposits in Canada. On the right-hand side is our reconstruction of the tagged hydrothermal mound in the middle of the Atlantic Ridge at 3.6 kilometers water depth that we actually drilled into back in 1994 to put that little story of that particular mound-style deposit together. The one on the right is about 250 meters in diameter and about 50 meters high. So it's a fairly decent size mound, about 4 million tons dry weight is the calculation for it. But the important part is we have mound, we have sheet or layered type deposits, and we also have a few that are pipe-like morphologies. And importantly, we have exhalation of the hydrothermal fluid to the seafloor, which we call the seafloor massive sulfide. But actually, most of the deposits and most of the big deposits are actually sub-seafloor replacement in their genesis. And I'll touch how and why that occurs as we go through the talk. As far as tectonic environments go, the two things you really need are A, it has to be submarine, and B, it has to be extensional. We don't know any of these types of deposits that form under fresh water, a lake or a river, or under glaciers or anything like that. They form in the seafloor. And they're actually a stock standard part of formation of ocean crust. And that ocean crust could be mid-ocean ridge, sedimented or unsedimented. It could be island arc, it could be back arc basin. It could be in the incipient rifting of continental arcs, such as the Red Sea, back arc basins there. But that's what you need, submarine extensional tectonics. What you find if you follow the literature in this, and those of you that were educated back in the 70s and 80s, especially into the 80s, is everybody came up with the idea that these had to be in submarine calderas. They don't. Some do form in submarine calderas, but the vast majority don't. They form on ridges, underwater, etc. And the other thing to appreciate in the modern seafloor is topography is not flat. There are mountain ranges, there are constructional tectonics, there's domes, there's arc volcanoes. Even the spreading centers have a lot of topography to them. So we have to take that into context when you understand how they form and where they form, especially when you're looking at the ancient rock record trying to discover these. As far as classification goes, there's many methods here, and I'm not going to belabor the point, but we have tectonic settings, as you can see there, that fine in a modern sense, but going back into the Archean and trying to understand if what we consider modern plate tectonics was operating then, and can you even recognize it? So that's one thing. The Canadians came up with this host rock classification where you either have mafic-dominated host rocks or bimodal mafic, et cetera, et cetera. You can read those for yourself. That can be useful, but it doesn't tell the whole story. Probably the worst classification type is the districts, where you name a deposit after an area where they were first discovered or where they're famous for. And I've listed a bunch there. That's the least useful. And the other one, the bottom one that I tend to like to use is based on the metal content, because that tells you a lot about how and why they formed, what metals are in them. We have copper dominated, we have copper gold, zinc copper, polymetallic, and even gold only styles of deposit. So the way I look at it, probably a combination of the host rock classification, the metals classification, really helps you understand what type and style of VHMS deposit you have. A diagram is colored dots on a colored background, which isn't particularly helpful. But what I want to do is, this is a diagram that Al Galli published a little while ago now, but it shows the distribution of VHMS deposits on the current surface of the Earth. And you can see that they're, apart from Antarctica, they're on every continent. There you can see. This is based on the Canadian designation of the colors of the circles there. The point is, you can see they're distributed all over the Earth, from the oldest rocks, the Archean rocks, up to the modern seafloor. Now, but what it turns out is the top 50 deposits, and that's based on the total tons of contained copper, lead, and zinc, are actually found in 7 districts on the Earth, because these deposits form in clusters. So we've got the famous Abitibi Belt that crosses between Ontario and Quebec in Canada, the Bathurst District in New Brunswick, the Iberian Pyrite Belt, huge volumes of mineralized rock expanding the Spain-Portugal boundary, Skellefteå District in Sweden, the Ural Mountains District, a very, very famous district, is that main mountain range running through the central part of Russia. Not a lot of people know about those deposits, but they are very, very large. And then the famous Kuroko districts, tertiary in age, beautifully preserved, but I can tell you they're actually very small. And then, of course, in Australia, we have the Mount Reid Belt, which has a number of big famous deposits and about 250 million tons sulfide or massive sulfide in the deposits there. So little Tassie punches above its weight once again with one of the great world's VHMS districts. And that's hence why I ended up down in Tassie. And I've spent, part of my life studying all the deposits on the West Coast. I mentioned that tend to occur in clusters. This is a diagram that Don Sangster put out in 1980. This was right at the height of everything had to be in a caldera. So that's drawn everything in a big, you fit anything into a circle if you draw it, funny enough. But the point is, these deposits do occur in clusters, The reason for that is we have the rock packages being laid down on the seafloor. We have extensional tectonics. There's been enough time for the hydrothermal system to develop and extend down deep into the crust, interact with the crust, pick up trace elements, sulfur, etc., become heated up, focus back up into sites of deposition. That's why these tend to occur in clusters. Sometimes you get a really big one and a bunch of smoke, but they do turn in clusters simply because we've got all the geology, geochemistry, fluid flow, et cetera, all organized right. And these things tend to occur relatively quickly in small volumes of rock. As far as the age goes, as I mentioned, these form all through Earth's history. We have deposits as old as about 3.48 billion years, all the way up to ones that are forming on the seafloor today. And you can see from the bar chart there, which is basically the ages and the number of deposits that have been found through this huge USGS database, which you can actually download for free, by the way, off the web. And it's about this at roughly 1,100 deposits. You can see there's peaks and troughs through that, obviously a lot more in the younger rocks, simply because we haven't eroded those down or they haven't gone down the subduction pipes yet or anything like that. But the point is, these deposits form during the assembly of continental land masses where we've had the initiation of spreading and then subduction happening. And it actually turns out that VMS deposits are one of the first things that tends to form in sort of the overall metallogenesis of arc systems. And it's important, though, if you're exploring or you're looking for a new land package in a new district, that you're getting into the right package of rocks, age-wise, that are part of this assembly of the continental land masses tectonically, to do your initial potentially exploration in there. Lots of other stuff goes on after that. We do know through the development of the Earth's history, we've had peaks and troughs when these deposits have occurred. And the biggest one is actually just around the Cambrian Ordovician time. Here I've just listed some of the famous VHMS deposits sort of around the world at time from the Archean all the way up to the modern seafloor systems. And apart from Beshi in Cyprus, I've visited or worked on all of these. So I've really had a fantastic exposure to this type and style of mineralization all through ages, et cetera. And I can tell you some of the rocks from the Panorama District up in the Pilbara of WA are exactly the same as things that are forming on the modern seafloor today. It's basically a style of mineralization that's worked all through Earth's history, and we're still forming them today. And tonnage. We do have some supergiant accumulations, which I pointed out there. You can read through the list. Rio Tinto or the Iberian Pyrite Belt is the big ones, but they're primarily huge accumulations of iron sulfide with some other metal with them. Whereas things like Brunswick 12 and Kid Creek are true polymetallic styles massive sulfides. If you look at that huge USGS database and just do some rudimentary statistics on it, the average tonnage and grade is shown there, about 12 million tons at that. Now it's almost a meaningless set of numbers simply because it's just an average of these 1,100 deposits. But the point is we're dealing with deposits that aren't very large. And you can see below that line there that 80% fall between 0.1 and 10 million tons and about 50% are less than 1 million tons. So we're not dealing with huge volumes of mineralized rock. What we tend to be dealing with is a bunch of metal packed into a small volume of mineralized rock, and that's what makes them attractive targets for some companies. They are generally copper, zinc, with always lesser amounts of lead and variable amounts of silver and gold. The way we tend to look at it, based on the group out of Tasmania, is we just use simple ternary plots, and these are being used all around the world, et cetera. This is just taking the average amounts of copper, lead, and zinc, in this case, the Australian VHMS deposits based back on our work in the sort of late 80s, early 90s that Ross published. And you can see, first of all, that you can divide them up into three types. There's the copper type, the zinc copper type, and the lead zinc copper type. The numbers that are crossing and making those divisions are what we call the zinc ratio and the copper ratio. The one thing that should be strikingly obvious to you is these things are never lead rich compared to the other metals. It's a peculiarity of this type, even though lead and zinc is transported virtually in the same conditions in the hydrothermal fluid. A lot of it has to do with source rock, but these are copper zinc deposits for the most part with some lead and precious metals in them. So if you get something that comes in with an awful lot of lead, very little bits of copper and zinc, 99% of the time it's not going to be VHMS deposit, it'll be something else, SEDEX or some other style of thing you've got, or a Mississippi Valley or Irish or something of that nature. But these are the metal conditions that we see in these deposits. Another way of showing that is this. This is sort of the contained tons of copper, zinc, or lead metal in deposits. And you can see there that the copper is variable. Zinc is always by far generally the greatest metal. There's a couple of small examples that aren't, but there. And then lead is generally the smallest amount, or sometimes it doesn't even show up in the deposits themselves. So these are known to be primarily zinc deposits with copper, lesser amounts of lead, and then, of course, the precious metals come into it. Now, this is a schematic cross-section of a VHMS deposit, and the reason I put this in is we deal with terms like footwall and a hanging wall. And we tend to use these in a stratigraphic sense, not a structural sense. We generally have a footwall package of rocks. There is a time break, can be short, but there is generally a time break to your hanging wall package of rocks, which quite often are a very different composition or nature compared to your footwall rocks. So the mineralization forms at a break. Generally, they're in the development of the volcano-sedimentary sequence in these environments. That break sometimes can just be the seafloor. Other times it's a whole pile of breccias, et cetera, in there. But the hanging wall package often is a very different package of rocks compared to the footwall package. You can see the alteration pipe cutting through there, and then various types of mineralization sitting above that. But I'll go into those in a few more slides. We did a sort of a run through of the composition of the footwall and immediate footwall and hanging wall rocks to the Australian VHMS deposits. And what we found was rhyolite is the most common footwall composition. That could be coherent, it could be volcaniclastic, but rhyolite was the most common composition. The hanging wall, however, generally is what we call the mixed bag of lithologies. You saw there is rhyolite still there. There's often sediment, there's andesite, there is basalts, et cetera, in there too. This just doesn't show up too well on the screen, or it does show up fairly well on the screen. But the point is, you do generally have these breaks of a thick pile of felsic volcanism, then everything seems to get its act together, hydrothermal systems, et cetera, going, mineralization forms, and then we get a very different character of volcano or volcano-sedimentary rocks sitting above the mineralization in the hanging wall. An example I use here is the Mount Windsor volcanics of Australia. These are Canberra Ordovician rocks. It hosts the famous Thalanga deposit, as well as smaller deposits such as Highway Reward, Liontown, Waterloo, Far West, West 45, et cetera, in there. But the point of this diagram is we've got a 1 to 2 kilometer thick package of the Mount Windsor rocks there. We've got the Thalanga package sitting on top of that, and then a deposit sitting on top of that. And then this package above it, as you can see, is what we call the mixed bag. There's everything from dacite to basalts to andesites to volcaniclastic rocks, et cetera. And the deposits up in there and can still form, probably at a slightly later time, but they're often smaller than the ones that tend to form right on the main rhyolite footwall package there. As far as the mineralization goes, these are mapped sulfide deposits, as the name indicates, and generally we're dealing with 50 to greater 95% sulfide minerals. And by far and away, the greatest proportion of that is iron. We're dealing with pyrite, pyrrhotite, or sometimes magnetite. These deposits are actually huge, giant accumulations of iron. We always talk about the sources for the copper, lead, and zinc, and silver and gold, and everything else that's in it. But actually what we have to have is a huge amount of iron and a huge amount of sulfur to form these deposits. It's a relatively simple mineralogy overall. Chalcopyrite's the main carrier of the copper, sphalerite for the zinc, galena for the lead. But there are lots of other minor amounts of oxides, other sulfides, sulfosalts, selenites, tellurides, et cetera. We can get cassiterite in these deposits. We can get molybdenite in these deposits. We do have lots of sulfosalts, the main carrier of silver, as well as other ones that can occur in there. Interestingly enough, what we are recognizing around the world is they're quite often late in the paragenesis of these deposits. We can get an assemblage of bornite, energite, tennantite, and covellite. And those of you that work in other spheres of economic geology will quickly realize that that's a high sulfidation assemblage of minerals. What we are seeing in deposits like Myra Falls or Kidd Creek and various others, that near the end of the formation of these deposits, we may have had a magmatic fluid coming into it that does create some advanced argillic alteration, plus this basically copper arsenic gold mineral assemblage cross-cutting through. And the little diagram on the bottom right is from Myra Falls showing that style of mineralization. The gangue in the deposits is a relatively simple assemblage of quartz, barite, anhydrite, chlorite, sericite, sometimes talc. And if you are in the right climatic environment, we can get supergene weathering on these deposits if they're at or close to the surface, which can, of course, increase, I should say, the economics of the deposits. What we tend to see in these deposits is zoning. And we'll see it with the alteration, and we certainly see it in the mineralization. We tend to have a copper-iron dominated stringer zone, which can have peripheral lead-zinc stringers in it. The base of the deposits are generally copper-rich, then it goes to copper-zinc. We drop out the copper, we get the lead-zinc, and we often get a sulfate capping to the upper parts of the deposit. It could be barite, could be anhydrite. Few instances it's gypsum, but it's where we tend to get more of the silver and gold in that lead-zinc rich portion higher up in the deposits. And that zonation is actually can be really important to help you understand when you drill into a system where you are, or if it's being dismembered, you can use metal zoning to put it back together. And basically, this is showing that distribution based. Now, if you've got really hot fluids, like say greater than 350 degrees, all you will get is iron, either pyrite, pyrrhotite, or magnetite, or a combination. You won't get any metal in it simply because the fluids are too hot for chalcopyrite to precipitate. It generally precipitates at lower than 350 degrees, even down to 300 degrees there. So we tend to have an iron-rich base to the deposits, quite often an iron mound, and then you get your chalcopyrite with plus or minus gold. Then you get sphalerite coming in, then you drop out the copper, get your lead zinc, you get your silver and gold higher up as well, and then you've got your barite plus or minus gold up near the top. So that's that zoning that we see, and there's really good reasons for why that occurs. But what's also important are the trace elements. When we're in our higher temperature copper-rich zone, this is where we tend to get things like cobalt, bismuth, tellurium, plus or minus tin or moly, as I've mentioned before. Whereas when you get up into the lower temperature, less than 250 degrees, this is where we get a very different trace element assemblage. You get arsenic, antimony, cadmium, mercury, selenium, thallium, etc. in there. Now, the antimony and arsenic are where the sulfur salts, they're the main players in the sulfur salts. The cadmium and mercury tends to be valerite. We do get our selenides, and thallium can either be in sulfides, the self-pyrite, but also in some of the potassium-bearing alteration minerals like sericite, or if you happen to have potassium feldspar, it can sit in that as well. The gold in these deposits is very important. Everybody's hunting for gold these days. If you want to find a good gold deposit, you'll either look for your copper zinc type or your polymetallic type. Your just copper type has sort of variable gold in it, but your copper zinc and primarily the polymetallics are where you're getting your best gold. As far as silver content goes, as you increase your base metals, you increase your silver content. It's almost a one-to-one relationship. And as I said, the main carrier is tetrahedrite. Or argentiferous tetrahedrite. If it's really, really rich, it's called fibrate. And in galena, and in certain instances, you can get silver in chalcopyrite at the same time. Now, as far as the features go in these deposits, the textures are really quite intriguing. There is true massive sulfide, which I call featureless, just a fine-grained interlocking mesh of sulfide minerals, and is generally very fine-grained when they first form. That's the upper photo there is of the Kuroko district, a photo taken underground in the famous Oko Wars there. And some of you younger people in the audience, that black thing on the side is what we used to use for scale. It's a lens cap from a camera. Many of you may have never seen one of those before, but most of us have had the last remaining photograph of a lens cap that we took, where we've left it underground somewhere. We have fragmental ores. On the seafloor wave action, these deposits tend to break up, they weather, with time, and we can get the currents moving things back and forth, or little debris flows, etc. And you can get graded beds of sulfide on the seafloor, and that's a beautiful example from the Kuroko deposit. These deposits are known for their banding. Now that banding can be primary, it can be replacement, or it can be deformationally induced. The photo of Q River there is massive sulfide that's being deformed, and generally you can pick it because the galena coarsens up, it's in seams, and in that particular sample from Q River, all that banding is actually parallel to regional cleavage. We do get internal or veining as well. We have weight, especially in sub-seafloor replacement deposits. And if you're really fortunate, because in a mound-style environment, we know we have all this fantastic hydrothermal vent fauna around the deposits. As you go back in time, that was still operating or still forming at the same time. You can actually get fossils. You can have the giant clams, you can have the mussels, you can have the gastropods. The little sample, the black one there with the pen next to it, those are actually fossilized tube worms. And the sample on the far right, that's a cross-section through a black smoker chimney taken from the Alexandrinka deposit in the Ural Mountains. Stringer zones are really important. They occur beneath the massive sulfides. They're cross-cutting veins and veinlets. They have vertical and lateral geometries, depending on the style of mineralization, and they can be economic. Quite often they're mined for copper and plus or minus gold in some instances. The Iberian Pyrite Belt, that's a beautiful example there in one of the photos. That's actually mined for its pyrite to make sulfuric acid. As far as morphology goes, we're dealing with two major types. We're dealing with mounds that have the underlying stringer zones. The Hellier deposit in Tassie is probably Australia's best example of that, with a well-focused pipe underneath it with zoned alteration with a massive sulfide blob sitting right on top of the pipe. Basically, if you find the pipe, you want to go up to where that may have got to a seafloor position, and that's where you're going to find your mineralization. And Mount Chalmers there is another example shown. By far more common, though, are these stratiform massive sulfides, these lens or sheet-like deposits that tend to have a much broader stratabound style footwall alteration to them. They're thinner, sort of aspect ratio. They're broad, but they're relatively thin. Here's a nice example just showing you there from Scuttles, but again, showing that the stratabound nature of the footwall alteration, we've got these thin lens-like zones of massive sulfide. And in these environments, you generally just don't have one lens. You have multiple lenses in the package of rocks you're exploring through, mostly because a lot of these are formed by subseafloor replacement. So you've got a greater volume of rock to be looking through instead of just a seafloor position where your mound would be found. As far as alteration goes, we have a large number of different styles in these volcanosedimentary environments, but generally when you're exploring for it or students are studying these for their theses, they concentrate on the footwall alteration, and again, those can have pipe or stratabound morphologies to them. It's a relatively simple association of quartz, chlorite, sericite, plus a variety of carbonates. We can get advanced argillic minerals if we do have acidic fluids into these systems, quite often late. And then, of course, the metamorphic equivalents. As you go back into the ancient rock record and things are being deformed and metamorphosed, we have to sift through what a quartz chlorite assemblage looks like is now amphophyllite with cordierite. So you got to deconstruct your alteration when you get into these higher metamorphic terrains. Hanging wall alteration is absent if the hanging wall was the ocean water when a mound was forming on the seafloor, or if it's being covered over while the deposit's still forming, you can get weakly developed hanging wall alteration. Or in the subseafloor replacement model, the whole package of rocks is altered, and you've got parts of it that are completely replaced that form your mineralization. The hanging wall minerals are a little bit different. The quartz, albite, chlorite, sericite, sometimes zeolites and carbonates, again, advanced argillic minerals, and of course, the metamorphic equivalents. But we could spend days talking about the hydrothermal alteration around these, but I'll just leave the alteration at that for now. And then what's also very important, especially in exploration, is the ore equivalent horizon. These are these stratiform exhalite deposits you may have heard of that extend at the seafloor position away from or around your massive sulfide. They're generally iron, manganese, and silica dominated, quartz with hematite, magnetite, and the various manganese oxides. You can get sulfides, sulfates, and carbonates in it at the same time. You can get just iron-rich sediment, just pyrite and shales. You can get sulfide-rich volcaniclastic rocks that occur in these. But what's important about recognizing these, that if you're in an area you're exploring, and you need to recognize if you actually drill through or prospect over potentially one of these ore equivalent horizons, that tells you you're at the right time break or the time in your volcanosedimentary development that you've had hydrothermal fluids getting out onto the seafloor. They may be above subseafloor replacement, or they're actually marking the position where a mound-style deposit is. So they're actually very important to recognize, and we can do that mineralogically, geochemically, et cetera, to pick that so you know that that's your more perspective horizon you want to be looking at or below as compared to other parts of your volcanosedimentary package. Here's some examples. Upper left is from the Newton Creek Spillway. That's a nice little quartz-rich Exhalite horizon there. The Abitibi Greenstone Belt's quartz magnetite, the Mount Windsor Belt, quartz hematite Exhalite in the Thalanga district, and then the Kuroko district, the famous quartz hematite Exhalite, or Tetsuzeki is the Japanese for it, sitting right on top of the massive sulfide, or the basalt sitting on top of that. They're important to recognize, but they can be relatively thin. As I mentioned, in the right climatic environments, definitely not Tassie, but say WA, for instance, you can have supergene weathering, just like we do in the big porphyry deposits, et cetera, et cetera. And you do get a very nice profile formed. You get your supergene oxide zones of your various colored carbonates, et cetera, oxyhydroxides. You get native copper. Then you get down into the supergene enrichment zone where you get your chalcosites, cobalites, et cetera. And then you move down into your primer protor down below that. And the best example we have in Australia that's been beautifully developed is the Degrussa deposit up in the Pilbara of WA. But that can be very important for the economics. Here's some information that Marty Hawk had in her thesis back a few years ago now. But, I mean, it was 1.6 million tons at almost 5% copper in a gram, in a gram gold. But some of the supergene sulfides was direct shipping ore. You can see that as 150,000 tons at 30% copper and 2.5 grams per ton gold. That material from out of this pit paid for a huge amount of the infrastructure at Sandfire's operation. As I mentioned before, we do get a bunch of different types and styles of this mineralization, and it's based around sort of these 5 points I've got here. One is the tectonic setting. If you're dealing with basalt-dominated mid-ocean ridge spreading, you're going to get a copper zinc deposit. There's those rocks, as the hydrothermal fluids go through it, have virtually no lead, very little silver, and sometimes a bit of gold, but you're generally looking for a copper zinc. You're more in a baric environment with a lot of felsic volcanic sediments, you're going to get a true polymetallic nature. The volcanic substrates I'll highlight in a few slides from now, but suffice it to say, understanding the makeup of the nature of your volcanic rocks in your footwall, whether they're coherent rocks or whether they're volcanic clastic and sediments, will dictate the type and style of deposit you get. The nature of the mineralizing fluids. We know we've dominantly got convecting seawater in these systems. That's the main hydrothermal fluid, but we do now recognize significant, or sometimes in deposits, a significant component of magmatic fluid. Often that brings in that late advanced argillic alteration and a high sulfidation style of mineralization. We have the temperature-dependent solubility controls. High temperature, we get our copper. Lower temperature, we get our lead zinc. And then, as I've mentioned, we have our sub-seafloor replacement and seafloor exhalation, and they will give you different types and styles of mineralization at the same place. The little diagram here is one we use basically to sort of understand the deposits in and around the Canberra Ordovician of Australia. You do have some deposits that are sort of more intimately associated with synvolcanic intrusions. A good example of that is Mount Lyell. These are intrusion-related copper-gold replacement. They're almost like huge stringer zone type systems with copper and gold in it. The pipe-like bodies there are more like the highway reward systems, which are actually in a coherent rhyolite-dominated package with focused fractures that have put the fluids up there. And we've got these massive pipes of pyrite with chalcopyrite in it, some small lead zinc lenses around it, but primarily pyrite, chalcopyrite. Then we have our classic polymetallic style mound like Hellier, the sheet styles like Rosebery or Hercules, et cetera. But also what we're recognizing in the development of these volcanosedimentary sequences is in some instances, we do get these shallow water, and that's near wave base, replacement zones. And a good example of that is Henty, which is primarily a gold-only deposit. There's a little bit of base metal in it, bismuth and a few other things like that. But it's actually a distinctive silicious replacement of a particular rhyolite horizon with a huge amount of gold in it. And we are recognizing these. There's some now recognized in parts of the Abitibi region, et cetera, and other parts of the world, these sort of shallow, potentially shallow water gold-rich deposits that we do throw into the bucket of VHMS. As far as the genetic model, two main ones, there's seafloor deposition, where we have seafloor exhalative systems, and a little diagram there sort of shows your focus fluid coming up, hitting seawater and dispersing and quenching basically, and that's the site where you get your mound formation. That fluid actually gets out into the water column and helps create our metalliferous sediment in and around these deposits, or an exhalite horizon there. And I'll go through this idea of zone refining in just a minute. The other major genetic model is subseafloor replacement, where we get cross-cutting replacement pipes, and we also get stratiform replacement of porous and permeable volcaniclastic or sedimentary units. And that really is why we get these lens-like deposits, because of subseafloor replacement, where our mounds are sitting right where the focused fluid comes up on the seafloor. Little naughty cartoon showing the whole idea of hydrothermal convection. Remember, the whole idea is we're in a submarine environment with extensional tectonics. So you've got fractures opening up. Cold seawater percolates down into the volcanic pile. As it's percolating down into the pile, it's interacting with the rocks, it's altering the rocks, it's picking up trace amounts of metal and or sulfur out of the minerals it's interacting with. At some point, there may be these synvolcanic intrusions or magma chambers sitting down below, which heats the whole package up higher than normal geothermal gradient. Those waters become heated up, they become less dense and buoyant and hot, and they are focused back up structures towards the seafloor. They rise towards the seafloor. On that path up, that's where we get our stringer zones on the way up, or stratobound zones. And then we have exhalation of the fluids onto the seafloor. In this instance, shown here with a beautiful black smoker from the Galapagos area there. But also appreciate, if we've got a big porous permeable package of rocks sitting on the seafloor, they're water saturated. So these may be focused up into that, but then they disperse in the rock pack. That's what creates our subseafloor replacement, both the mineralization and the alteration. So in the mound, basically the point of these sort of diagrams is to show you is these deposits just don't form in one hit. They tend to form from an evolving hydrothermal fluid with time and with temperature. They start out coolish, as you can see here. We're building up a bit of a stockwork zone with some lead zinc in it. Then we're coming up to, it gets a little bit hotter. We're starting to see chalcopyrite form, which is that orange zone down below, lead zinc above it, and then barite above that. And basically what happens in this case, it's replacement. The hot fluid comes in contact with a mineral assemblage that formed at a cooler temperature and actually dissolves it back into the fluid. You're replacing it with, in this case, chalcopyrite. That fluid moves up and cools, and the lead zinc deposits again. So you're actually, these things grow basically through replacement within themselves. And then if all the way to the end stage here, we've got the really orange material down at the bottom is just pyrite, then chalcopyrite, and lower grade lead zinc, higher grade lead zinc with some of your sort of zones on your sulfates, et cetera, on top. But the point is, this is with increasing time and temperature. And what we're left with is sort of a snapshot at the highest temperature point that the deposit went through. If fluids get down, cool back down, et cetera, or the sort of cooler fluids are coming through it, you'll get veining of lower temperature assemblages through the higher temperatures, but they don't redissolve and go away necessarily with that. And this is what we call the zone refining model. And we do see this phenomena sometimes in stratobound deposits, but mostly in the mound deposits. So you can think of your metal zoning as a poor man's geothermometer in these deposits. And these are based all on geochemical solubility relations, et cetera, et cetera. So your basal pyrite mounds greater than 350, all the way up to your high-grade lead zinc is around 200 degrees. So you do have these rapid temperature zoning. And I've seen this occur over a couple of meters in drill core and on rocks we picked up off the seafloor. You'll also see it in black smoker chimneys themselves. The best example of mound-style deposit we've got in Australia is Helier. In this case here, it's a mound. If we start at the bottom left, that's the pyrite chalcopyrite, very fine-grained material at the basal part of the mound. Then coming into the large panel next to it, this is pyrite replacing earlier formed sphalerite. And that's actually a chunk of rock with the zone refining model in snapshot. You can see the pyrites coming in and taking out the darker sphalerite and cross-cutting through it. We had whole stopes of this underground at Helier, which is spectacular. Then we move to the veins next door. How you move the fluid up through your previously formed sulfide is fracturing, veining going through. Sometimes they're trapped in there, or basically that. You can see the veining cross-cutting through that particular stope. It's an underground photo from Helier. Then we have the banding that you see in many massive sulfides. Then as we come up the right, we have a barite-rich horizon sitting on top of the massive sulfide, and that's a plate, underground rock bolt plate for scale. And then we've got, Helier was interesting, we actually had a siliceous cap, which is like the exhalite, sitting right on top of the uppermost part of the massive sulfide. And that was laminated quartz, dark quartz, and pyrite with elevated gold values sitting on top of it. Helier's got an andesitic footwall. It's got a basalt sitting on top of it. The basalt trundled over the top of Helier when it was still forming, and that's why we've got a hang wall alteration plume sitting above it. The hydrothermal system hadn't finished operating. The fluids went up through the deposit, up into the basalt, and created a hang wall alteration plume. The subseafloor replacement style of mineralization is shown here. There are some really distinguishing criteria that you need to look for to prove that you've got this going on. One, that the mineralized intervals are enclosed within rapidly in place volcanic or sedimentary facies. There are relics of the host facies within the mineral deposit, which is basically incomplete replacement. You do have replacement fronts between the minerals or the mineralization of host facies. The deposit can be discordant to bedding, and we've got strong hydrothermal alteration all around your zone of mineralization. It turns out criteria 1, 2, and 3 are really diagnostic of subseafloor replacement. 4 and 5, we can get various things that can happen in different VHMS deposits. Well, if you get 1, 2, and 3, you know you're dealing with subseafloor replacement. Here's a nice example of some rocks from the ridge deposit in the Myra Falls district in British Columbia. And this shows fragments of the host. It was a polymictic volcaniclastic rock. You can see the sulfide cutting through it. And a couple of things. One, you can see some of the fragments have alteration zoning in them. And you only get that if they were sitting there and those hot fluids that precipitated the sulfides came in through that package of rocks. There's other places there you can see almost incomplete replacement of some of the fragments. And what you look for is really wispy, delicate edges. That's not going to survive transport underwater, but that's the sulfides eating away at those various fragment types. And often the felsic ones go first and some of the really mafic ones. Coherent rocks are harder to go. Pumice goes easily, and so do the mafics. Here's a nice set of core from the Currawong deposit in Victoria. This is a package of rocks. At either ends of the core, you have your relatively unaltered felsic volcaniclastic rocks with some sediments in it. And then you've got various zones of semi-massive sulfide, stringer, and massive sulfide that goes in and out as we've got subseafloor replacement through this package. So, which brings me to this idea of the volcanic facies control. This is really quite important. That in a little diagram on the left shows an impermeable footwall, lavas or domes. To get the hydrothermal flow of that, you have to have a fracture, a fault system. The fluids are focused up to a point of discharge. That's where we get our pipes underlying it and our massive sulfide mounds sitting on top. Conversely, on the right-hand side, if you've got porous permeable footwall, which is epiclastics, volcaniclastics, something like that, pumice breccias, you may focus your fluids up into that package, and once they get into that package, they will disperse. And that's here we get a lot of dissemination, semi-massive sulfide, but if it's really quite concentrated, we can get our more massive sulfide lenses or sheets in that package of rocks. This little diagram shows that at seafloor that can happen. More often than not, it's actually replacement within that porous permeable package of rocks where you get your mineralization. And just another couple of slides to highlight this. And it's really important for explorers too, to realize what type and style of mineralization you're going to get depending on not only your composition of your volcanic rocks, but your nature of your volcano or volcanosedimentary rocks got there. And you can read the points there. I won't go back through them ad nauseum. And then the whole idea of the volcaniclastics. Now, in this scenario, this increases your exploration space. You need to understand your volcanic stratigraphy, et cetera, what your package is, where your fluids may have gotten into it. And then you have to adequately explore it. You're not just looking potentially for one horizon here. You've got an enhanced exploration space through that package of rocks. We see that at Rosebery deposit. We see it at many other deposits around the world, that you've got mineralization over several hundred meters within that package potentially. So you've got to have basically enough drill budget to test all this, get down through that package to see if you're finding mineralization. We have ways of dealing with the alteration, mineral chemistry, et cetera, to give you hints where you are in a system if you're getting closer or further away. But it's important to be able to explore through that package to potentially make sure you haven't missed something. Okay, genesis, just coming back to the fluid chemistry. If you look at your mineralization in these deposits, or pyrite, pyrrhotite, chalcopyrite, or quartz, chlorite, cerussite alteration, they form from modified seawater that's been circulating through a rock package. And if you're thinking about your other terminology, the sulfidation terminology, these are low to intermediate sulfidation fluid conditions. Same thing you find in some of the epithermal deposits, except here we're dealing with seawater, not meteoric water. At the same time, we do find advanced argillic alteration with high sulfidation style mineralization. And these come from the high sulfidation fluid conditions. These are more magmatic, they're more acidic, etc. So we have both interplaying in these deposits at different times and different deposits, admittedly, but they both can occur. Which sort of brings me now down to the exploration side of things. I'm just going to tell you some of the things I think that are important and sort of work I do with companies to help them come up with better exploration models, etc. The important thing is to map, to prospect, and observe. Look at the rocks, see what they're telling you. What you're looking in the big picture are extensional tectonics, marine volcano-sedimentary sequences, geochronology. In the big picture, you're in sort of the right package of rocks you want to be. But also importantly, we're recognizing in these districts, there's often a timeline where everything is just right in the district. For instance, the Mount Read volcanics, we did a big study there, and it turns out that Hellier, Q River, Mount Lyell, Rosebery, and Hercules all formed at 500 million years, plus or minus, not very much, but they're in very different rock packages throughout the belt, but they all formed at the same time. And that's what happens. We have to get away from this idea of railroad stratigraphy across large tracts of land in these environments, because you've got constructional features, you've got arc volcanoes, you've got sedimentary troughs, you've got basins, you've got all sorts of things going on, but it's the time factor when everything's right is what you're looking for in there, not necessarily just one package of rocks. Structure and post-mineralization deformation is very important. Hydrothermal mineralizations, great to help you find these. Noting down if you find stringer versus massive sulfide is always good. The ore equivalent horizon and their features are vital in helping you pull apart where you are in your stratigraphy if you're at the right horizon. And then, of course, metamorphism can overprint all of this and can change your mineralization, grain size in particular. It can move things around a little bit with remobilization. We get a whole new package of minerals in the alteration, etc. As far as geochemistry goes, we've gone leaps and bounds in the litho-mineral geochemistry, how that can help us. As far as just general exploration goes, it's stream sediment, depending on your environment, of course, heavy mineral concentrates, the regolith, say in places like WA, that's well understood what you're supposed to be sampling. Gaussins and their geochemistry is very important. If you happen to work in the Northern Hemisphere or in places in high altitudes, you may have glacial till. Lake sediments can be useful, soils, soil gases, even biological. People are snipping tops off trees and plants and analyzing those. A lot of these are useful. The SWIR technology and the portable XRF technology that come in has been a huge boon for us. We can now, in rapid real time, get information on the alteration minerals, their chemistry. We can use that in zonation studies, et cetera. It's useful. The portable XRF, if it's like anything else, if it's calibrated correctly, is a fantastic tool where now you can do things like titanium, zirconium. You can get those analyses, do your ratios, understand through your alteration if you're dealing with a rhyolite, dacite, a basalt, or an andesite. You can also use things like the rubidium-strontium ratio from PXRF data as a proxy for the classic Ishikawa alteration index. So we're developing a lot of proxies and tools now for rapid identification of and in gathering information we can use. And of course, the whole factor of geometallurgy, understanding your mineralization, your mineral chemistry in your deposit. Can you actually mine this thing? I mean, is it so full of arsenic that you're going to have problems? Or is your sphalerite so rich in manganese you could have a problem? So understanding your mineral chemistry and your geometallurgy is very important early on in the piece too. And then, of course, we have geophysics. And these deposits, because of their nature, are great for geophysics. Magnetics and electromagnetic techniques are fantastic. They've been dramatically improved with time, especially the EM techniques. Electrical, the chargeability for your more disseminated style mineralization around the edges or pipes, et cetera, are very useful. Seismic gravity can be useful in the big picture to put you into the right package of rocks, especially in folded faulted terrain. Radiometrics, I think, is often underutilized, especially if you're dealing with a lot of potassium alteration, sericite-rich zones, et cetera. Radiometrics can help us. And oddly enough, in a few deposits, uranium pops up. It doesn't get talked about a lot, but it does pop up. And of course, these can be airborne with the classic planes or helicopters, but also now drones are coming into it, where we can have very small, tight surveys in areas with drone technology. And then there's ground and, of course, downhole geophysics at the same time. But no matter what you do, you got to drill. You got to get into the subsurface and find out what you've got. I mean, we have some deposits that stick out of the ground, but not very many. We have to use all sorts of other techniques to put us in the right area and then drill. As far as exploration potential goes, this style of mineralization over the years has been relatively unattractive for the majors simply because of their size. As I mentioned before, they're not all that big, but they're polymetallic. They're now a real attraction for the mid-tier, the juniors. Basically, we went, and the reason we're now got people coming back into these environments is when I came out to Australia in the late 80s, it was the time of the bulk gold, and everybody went off for bulk gold, chasing that. Then the porphyry epithermal boom came in, and everybody wanted the 4 billion tons at 0.1 to make a company out of it. And people literally forgot about VHMS deposits a lot of the time at that. But as I'll point out in a couple of points here, they've come back. We can have exploration success. We understand the ore deposit and exploration models around the style of mineralization pretty well. There's a lot of things that work very, very well you use to get into the right environment. But there are new discovery opportunities. As I mentioned, we're developing better genetic and exploration models with the advent of a lot more information, the SWIR technology, the portable XRF, some of the other things we're doing. We're getting deeper penetrating and better downhole EM to find these deposits. I think there's large tracts of deeply weathered Archean and Proterozoic craton that needs to be reevaluated now. Have been not gone over in the same instances some of the younger terrains have gone. There are known districts that don't have much cutting edge exploration. Most of these are in some of the more developing countries or centrally planned economies, as far as we can tell. There are emerging districts. Look at the success Sandfire had with Degrussa, and then Monty was found. And now the whole Briar Basin, you can't get a piece of ground out there for love or money. And a lot of people are exploring through that. I mean, there was Horseshoe Lights. There was a small deposit there known before, but people are going in and sort of, looking around that. But also what's happening is the revitalizing forgotten districts. A great example is the Mount Windsors. And I'm not spruiking one particular company, but this was an area that basically time forgot. And I know there's one member of the audience there that was intimately involved in exploration, at least one up in that area. But it was booming in the 80s, early 90s, and then it would almost just got forgotten about. People left. And it sat there for the longest time. There were a couple of small companies that played around and went bust. And then one particular company picked up the entire belt, all the mining and exploration leases, and a mill that was on care and maintenance for $6.5 million with resource in the ground. And they're making a go of it. That's Red River, for instance. And we know that other things like Mount Chalmers, for instance, now there was just a thing from Q Mines coming out that they're drilling around Mount Chalmers again. So there's lots of places are going back in. Peel Mining south of Cobar. The Benamber district is having another evaluation on it. Woodlawn, Heron Resources there. And people are also going back and looking at the tailings and seeing what opportunities for metal might be in tailings, especially for the older mine deposits, because they didn't really recover a lot of the gold because of the gold price at the time. So there's a sort of a reevaluation going on, both in districts and tailing piles. So in conclusion, just to wrap this up, these are VMS deposits are a big family of deposit styles I hope you appreciate. You need to understand your geology, your geochemistry, geophysical signatures. We have fantastic geology from the stringer zones up into your various massive sulfides, et cetera. But also what's really nice is we can go onto the bottom of the modern ocean today and see these forming in real time in front of your eyes. The black smokers and the white smokers are basically what you would get on top of your lower or your high-grade lead zinc. It's the lower temperature of the white smokers versus the high temperature black smokers. But it's really fascinating to be able to go and see this mineralization style forming in front of your eyes. As I've mentioned, it's one type of mineralization that has been forming all through Earth's history. So just a little bit about me. I am a consultant now. I do training and short courses for people, office, field, or internet on VHMS or epithermal deposits. I also do field to desktop consulting on that style of mineralization, as well as hydrothermal alteration in general. I can help you with geological and data interpretation. And I have been asked to review exploration programs and help companies with target generation, because also what's happened over the years, because everybody else went off for porphyry epithermal, apart from a few places around the world, they didn't train many people that were really au fait with VHMS deposits. And now companies are picking up ground and they're bringing in people like me and some of my colleagues to help them with exploration, simply because they haven't had the expertise or experience in their training to look for this style. So I can help you if you think, and there's ways of contacting me up there or through LinkedIn. So finally, thank you very much for your attention, and I'm happy to answer any questions.
Thank you so much. That was unreal, so interesting.